Hey guys, Sebastian from Madrigal here. Welcome back to this second part of the video series where we try to create a quick and dirty Vulkan backend for the game engine basis. If you haven't watched the first part, be sure to do that first to get some context. Okay. One thing before we continue, I figured I should talk a little bit about shaders, because whenever you actually switch from a graphics API to another one, how you actually manage to get your shaders working with the new graphics API tends to be kind of a problem. And in my case, it's actually surprisingly simple. So if we have a material here, let's create a very quick and dirty material. In the vertex shaders, we put a vertex shader input, we put a vertex shader output. We need to somehow transform that position, and we wire it out like this. What do we do? Maybe we need to do some normal as well. And I don't know, maybe a UV coordinate like this. Like so. You can see the code generation currently doesn't work. You need to put in something on the pixel shader side as well. Let's put in a pixel shader input. We put in a pixel shader output. And let's maybe just create a color vector, and we wire a color out into the output. You can see that, okay, we have some warnings here, but now the code generation works. So what this node graph does is it generates shader code, which looks like this. And this code is HLSL, High Level Shading Language. And HLSL is perhaps most widely used as the DirectX shading language. And it's compiled into DX bytecode. Let's see if I can I draw this out for you? Let's try something new here. Right. Okay, so we have HLSL, right? This is what we start with. And we compile this into DX bytecode. And DXBC is what the older DirectX runtimes, such as the D3, D11 runtime that we're using, expects and works with. So this is D3, D11. Right, but then we have something called metal, which we quickly covered, we're already supporting. And what does this expect? Well, it expects the shaders to be written in metal shading language, or MSL. And then this gets compiled into some kind of runtime representation, and that gets fed to the metal backend. So how do we actually get from here, from the HLSL one into MSL? Well, we use something called SPIR-V cross. And if you remember from the last part, we actually use SPIR-V cross in the VEZ library as well, which we'll be using today to actually get started with Vulkan. And SPIR-V cross can actually output metal shading language. That L got a bit weird. Right, so SPIR-V cross can output metal shading language, which we can then compile into the runtime forward and feed it to metal, and that works. But how do we get from HLSL to SPIR-V cross? Well, SPIR-V cross expects as the name suggests, I think it's actually, you're supposed to type it like this, SPIR-V. And SPIR-V is like an intermediate format that you can feed into SPIR-V cross. You can also feed it into Vulkan. So we have Vulkan here. And this guy can actually consume SPIR-V. And typically what you actually use to create SPIR-V is GLSL. So the GL shading language, which is kind of considered to be the official shading language for OpenGL and Vulkan and other related technologies. But we're actually just compiling HLSL straight into SPIR-V to get down to here, to the MSL and metal part. And so all of this works out really nicely for us in this Vulkan video episode now. I'm just going to move that down ever so slightly. Boom. All of this works out really nicely for us, because this means that we actually already have SPIR-V interpretation of all of our shaders. And I've had it all along. I initially created this SPIR-V compilation phase for the previous time I used Vulkan. And I sort of left it there when I deprecated that Vulkan backend, because this just basically worked and kept working. And later on it was then used to do the SPIR-V cross-pass, compiling the metal shading language and then feeding to metal over here. So this whole path has been there all along for every shader, unless you specifically don't want it to compile into SPIR-V, it does. And so that means that we have essentially SPIR-V representations for all of our shaders. And not only do we compile it into SPIR-V, we actually store the SPIR-V in the runtime shader file as well. So we can just consume this and feed it straight into Vulkan like this. So with a little bit of luck, this should actually work straight out of the box. We shouldn't have to really do anything to our shaders, which is like a really big help. And one thing that VEZ does for you is it consumes GLSL directly. You can see here in the official. Let's see, can I make this a little bigger? Maybe it is a little bigger. I don't know. Maybe it's a bit clearer at least. This is pretty small. I hope you can make out these texts here. But here they have GLSL, which, as I mentioned, is the official shading language for OpenGL and Vulkan. You're supposed to run it through the SPIR-V tools, produce SPIR-V, and then feed it into Vulkan. Well, for the VEC, they have essentially sort of made away with these two steps here. And what they basically mean is that you can feed GLSL directly into VEZ. My fork of VEC actually has a flag which allows me to just turn off the GLSL compiler completely, because I always feed precompiled SPIR-V directly into VEC. So if you use my fork of VEZ and you want to feed it GLSL, just make sure you set that flag in the CMake settings. Okay. So that's shaders. That's how we're going to deal with shaders. So should be really, really simple in this case. And depending on how you actually, if you're doing something similar, depending on how your shaders are set up, you might have to do more or less work than me in this case. Anyway, with that out of the way, and with a little bit of coffee, we can shut this down, and we can go to here. So in the last part, we basically took our metal backend and renamed the files to basis render device VK instead of basis render device metal. And what I've done since last time is that I've essentially removed all the metal stuff from these classes. So you have a buffer class here, for example. You just have the essentially the skeleton of it. So you can see this buffer VK class that we're going to create. It derives from GFX API buffer, and GFX API buffer obviously has some methods that you need to implement. So I think I have everything here. I haven't tried to actually build this yet. I think I have everything here that the GFX API classes expect. So with a little bit of luck, we should be able to actually compile our new VK backend, our new Vulkan backend, right away. So let's go through what we have here. So we have a buffer, which we looked at already, for keeping things like vertex buffers, index buffers, that kind of stuff. We have a backend class, and this class is essentially the link between our backend and the graphics engine, which sits in the core basis engine library. So you need to be able to somehow sort of hook this into the system, and this backend is part of that. So I've created a new type for it here in the core library, GFX backend type VK. This is just essentially an enum. I can show it to you in a bit, and I've changed this to Vulkan, and some strings there as well. But there's essentially no Vulkan code here yet, and this is also very empty. Some exports. This is a DLL. We don't really we link to this dynamically rather than statically, but we have some exports there as well. We need to export a few functions. Essentially here we have them. So the basis plugin system requires us to have a few things. We need to have these extern C functions here that the basis engine calls when this plugin is created, and it then creates, as you can see here, a new instance of this GFX API backend VK plugin class. Here we have some GLFW code, which I just copy pasted directly from the metal one. Everything is essentially except this one, which the GLFW documentation says that we should check. If GLFW doesn't support Vulkan, then we can just exit here. Right. And then we terminate GLFW when we destroy the plugin. And then we have some actually registering the backend here. These are things that work exactly the same on all the rendering backends. And yeah, nothing interesting here as well. Pipeline state is the next interesting part in the graphics API. So we're going to come back to pipeline state a little later, but this is one place where I think I'm actually going to have to eventually change VEC a little bit, because it's kind of counterproductive to how I would like it to work. Let's have a quick look at the D3D11 pipeline state. Actually, let's go to render context and bind pipeline state. I think it is, yes. So when you bind a pipeline state in D3D11, you can see that we have to call all these things to set the correct state. And with the more recent APIs like Vulkan, you essentially bind all the pipeline state in one go. And because I've kind of anticipated this, I've collected all of the state here in the GFX pipeline state under these where do we have it? Pipeline state description is right there. Yeah, it has all of these. It has the primitive topology, depth stencil description, rasterizer description, blend description, everything sort of collected in this description. To create a pipeline state, you have to fill in this description. You have to fill in all of these things, and each one of these guys has more data to fill in. And the idea here is that when you bind a state, a pipeline state, it knows everything that goes into defining that state, and it can bind it all in one go. And this is how Vulkan actually works. But VEC changes it. So let's go have a look at the official documentation for VEC a little bit. This is actually, VEC is pretty nicely documented, and I bet we'll actually want to look at this a little bit later. But yeah, so where do we have pipelines? Pipelines is here. So it says VEC alleviates the need to specify any of this information, so all of this stuff at creation time. And you can essentially with VEC just set some of this state later on. And this is sort of counterproductive because Vulkan wants to set all of this state in one go, and actually Basis GFX API wants to set all of this state in one go. So it's sort of silly that we have to split it up because VEC wants to split it up. So it's probably a place that I want to actually go back and change later on. But anyway, we have the pipeline state VK here, no members yet. It's just kind of empty. Here we have the render context, and this is the place this is the class that actually does the actual work. When you've set everything up, you've created your textures, your buffers, your pipeline states, your shaders, your everything. Then you feed it to this guy. You bind it here, and then you draw. And again, everything is empty. This is where we're gonna fill in things. We have some timers here, and I didn't actually touch this almost at all from the metal one. This actually wasn't implemented on metal, and you can see something like D3D11 code here still from the D3D11 version. So yeah, we probably don't. We're not gonna implement this on Vulkan either, at least not right now. Then we have the render device. Again, I've taken everything away that was metal related. I've had some forward declared classes here. I essentially left them in. I just renamed metal to VK, and that should be good. So there's actually some code here. Like if you create a render target, it will actually create a render target VK, call init, add reference, and return it. And this is the same for all the render backends, which is why I've left it in. So just like in DirectX, the GFX API objects are reference counted, so we add a reference here and then we return it, and then when the reference is 0, it kind of destroys itself. That's how it's supposed to work. But other than these create things, just returning newly created objects of the correct type, there's really nothing here. And just like in metal, with the HBAO+, which I covered last time, we're actually returning null. So we're not going to do anything about that. Here we have these getCaps capabilities. This is a way for the rendering backend to sort of report its capabilities to the core engine. So yes, we have tessellation shader support. At least Vulkan is supposed to support them. We also have geometry shader support. Partial constant buffer update support. This is something that may or may not be present on D3D11, but we have it here. And I set this HBAO plus support to false for now, so it's not even going to try to create like a context. Right. And some back buffer formula. I just copied this directly from Metal. Let's see how it works out. Render target. Nothing complicated here. So then we have the render window. This is essentially GLFW code. There's very little, if any, Vulkan or Metal or anything code in here. It's mostly just. Actually, is there any Vulkan code? Let's see. Vulkan can't be found at least. But this is setting up the window with GLFW. And essentially that's it. So I mostly left this as is. Shader program. Currently very empty, but we'll get back to that after a while. I know that the description has a vertex format, so actually I've left this line in, and I know that's going to be the case, so I left that in as well. Staging resources, I just commented these out. I don't know if we'll actually need staging resources. Typically you use a lot of staging resources on Vulkan, but I don't know if we're actually going to need them on well, this time around, since we're using VEZ. So I don't know. I just commented everything out here because I don't know exactly what's going to happen. You have these MTL buffers. These are actually the metal ones. So I don't know. They're there. Don't need to care about it right now. Here's a call. I've tried something out clearly. I'm not exactly sure. Here's like a VK device wait idle. Yeah, that's. I've kind of copy-pasted things around here, and we'll see. Maybe we'll actually want that there, but I'm not sure. But the swap chain is kind of related to the window. It is how you actually get things onto the window itself. And it's supposed to be much easier to work with VEZ than with raw Vulkan. So we'll have to look at that. Texture sampler, nothing here. Same thing with the texture, except I've left some parts here that I know are going to be kind of the same as with the other ones. So again, we're deriving from a texture, and it expects us to have certain methods here. This read data actually is pretty much copy-pasted from the metal one. We don't actually support reading data back from the GPU into CPU memory on metal currently, and I don't think we'll need that for Vulkan either right now. It's only used by the tools, not really by the game itself. So if I want the editor to work with Vulkan, I'm gonna have to implement this, but I just put a comment here to how we might actually want to do that later on. And yeah, when we create, we only support 2D textures for now, because that's how it is on metal as well. And then we call create 2D. If we are creating from a DDS buffer, so this is what I mentioned last time about us using this this DDS texture loader, which is like the Microsoft provided code that I've created all of these different versions for all of the different APIs, and I've tested this with the VEZ samples. I know that it works. So if we have a DDS buffer, we can just call that and create an image. And I copied this from the test that I did, but that's not going to work because we don't have the VK image yet, so we're going to have to actually put that in. If we don't have an DDS buffer, we go to else, and we'll get to create that ourselves. And yeah, no private members. And then we're reaching the end here of our tour through our backend. So we have this conversion CPP file that I mentioned last time. I commented out one of these guys because we're not really going to have any descriptor types. This is from the old metal backend that I created for Basis some years ago. And we're not going to work with descriptors directly because we're using VEZ, so I just commented that guy out, but other than that, it's exactly the same as before. So we just take a GFX API enum, essentially, blend operation, for example, and we turn it into a Vulkan one. And you can see exactly the same thing. We go to type conversion D3, D11, blend op. We have exactly the same thing. We again have the GFX API, but then we have a D3, D11 blend op add. And here we have a VK blend op add. So it's just a way to to map these commonly used types into the values that the backend expects. Finally, we have VK. So I have this header that I typically use in these backends. So I have here like include Direct3D 11.1 in this case, and then some common things here, and I have like a similar thing for metal, and we're gonna do the same thing for the Vulkan one. Actually, let's go. Maybe that's the first thing that we'll actually want to do here. So let's go to the metal one and let's see what does that look like. So yeah, we include the GLFW stuff, then we import metal from here. Yes. Okay. So something a little similar probably, because using GL framework or GLFW for this one as well. But okay, let's see. Let's see. I probably have to convert. I've done so many small changes to my Vulkan backend files here that I better recreate the CMake project just in case. Like so. And maybe we'll start with this Vulkan header here. This one. So if you go to GL framework Vulkan, right? Vulkan guide. Yeah, so they want us to actually include the Vulkan header, define this. So we take that and we put it there, and that should be fine. And then we should include the VEZ header as well, since we'll be using that as well. And then if we go to the metal one, we have this metal max frames in flight. We'll definitely want that as well. We have to do like a little bit of synchronization ourselves this time around. So VK max frames in flight is 3. So that basically means that when we are rendering, we can issue commands to Vulkan, which in turn issues commands to the graphics card. Then we don't need to wait for the graphics card to be done with its thing. We can immediately start working on the next frame, because it will take some time for the graphics card to actually finish its work, right? So that means that we will have actually several frames sort of being worked on at the same time. And 3 is typically what I've been using. I think that's what most people use. So we just set the define here so that we can actually we can change it if we want to in one place. So let's see if we can actually build this guy. Let's do project only and maybe a rebuild. I may have tried something previously when I did the cleanup. API entry, macro redefinition. This is perhaps not really a problem, but I might want to actually look into why this is happening. Anyway, I think we'll actually stop this. We'll actually end this part here because we did cover quite a lot of things, and this means that in the next part we'll actually get to write our first Vulkan code immediately without doing anything else. So seems like a pretty good place to take a break. Anyway, hit all the buttons, like all the smashes, do all the things, and I'll see you in the next one. Bye.